Morning fog clung to San Diego Harbor on September 20th, 1942, as Lieutenant Commander Eddie Sanders walked across the tarmac at Naval Air Station North Island. His destination was a heavily guarded hangar where something extraordinary waited. The instrument panel would be in Japanese. The controls would feel alien. The entire aircraft would smell of oil and unfamiliar materials that belonged to an enemy thousands of miles across the Pacific. Armed guards had surrounded this hangar since the precious cargo arrived 3 weeks earlier, their orders absolute. Sanders was about to fly the most valuable aircraft in the world. He had spent hours in the cockpit already, memorizing every gauge, every switch, every detail of the foreign fighter. But sitting still and actually flying were entirely different propositions. Intelligence reports suggested this aircraft was faster, climbed better, and turned tighter than anything America had. If those reports were wrong, or if hidden damage existed from the crash that brought it here, Sanders might not survive the morning. The Mitsubishi A6M2 Model 21 fighter sat in the hangar like a captured dragon, its secrets about to be revealed. The story of how this Japanese Zero came to rest in California began 5 months earlier, thousands of miles north in the Aleutian Islands. June 4, 1942, would be remembered as the day American dive bombers destroyed 4 Japanese aircraft carriers at Midway, fundamentally altering the Pacific War's trajectory. But while that titanic battle raged, a smaller event unfolded in the Aleutians that would prove equally transformative for American naval aviation. Flight Petty Officer First Class Tadayoshi Koga was 19 years old when he launched from the carrier Ryujo that morning. His orders were simple enough: strike the American base at Dutch Harbor alongside his wingman, Chief Petty Officer Makoto Endo and Petty Officer Tsuguo Shikada. The diversionary attack on the Aleutians was meant to draw American attention away from Midway, and Koga's unit executed their mission with precision. They shot down a PBY Catalina patrol bomber and strafed survivors in the water, demonstrating the Zero's deadly efficiency against anything the Americans fielded. The lightweight fighter performed exactly as its designers intended, faster and more maneuverable than the enemy's best. Then everything changed. A single bullet from a .50 caliber machine gun, fired by a desperate American gunner who would never know the consequences of his shot, struck Koga's aircraft. The round severed the oil return line. In an engine dependent on precise lubrication, this represented a slow death sentence. Oil began spraying from the damaged line, and Koga's combat experience told him he had perhaps 15 minutes before the engine seized. He radioed his flight commander about the damage and turned toward Akutan Island, 25 miles east of Dutch Harbor. Japanese planners had designated the island as an emergency landing site, and a submarine waited offshore to rescue downed pilots. Approaching Akutan Island, Koga spotted what appeared perfect for an emergency landing: a long stretch of flat grassland half a mile inland from the coast. His wingmen circled above as he extended his landing gear for what should have been a routine wheels-down landing. Shikada, flying overhead, made a second pass and noticed something that filled him with dread. Water glistened between the grass stalks. The field was actually a bog, grass concealing knee-deep mud and standing water. He tried to radio a warning, but Koga was already committed to his approach. The Zero's wheels touched grass at approximately 80 miles per hour. For one brief moment, the landing seemed successful. Then the main gear sank into soft mud beneath the vegetation, catching with tremendous force. Physics became an unstoppable executioner. The lightweight fighter's tail was still traveling at landing speed, and the sudden stop of the main gear caused the aircraft to flip completely over in a violent cartwheel. The Zero slammed upside down into the bog with bone-crushing impact. The force snapped Koga's neck instantly. His body remained suspended by his seatbelt in the inverted cockpit, service pistol and samurai sword still strapped to his waist. Flight suit pristine except for medical taping wrapped around his torso from previous injuries. Above, Koga's wingmen faced an agonizing decision that would alter the course of the war. Standing orders required them to destroy any disabled Zero to prevent capture. They circled the crash site multiple times, machine guns ready, searching for any sign their comrade had survived. The aircraft appeared remarkably intact, sitting upside down in the marsh like a turtle on its back. They could not bring themselves to fire. Perhaps Koga was alive, trapped, waiting for rescue. Murdering their friend on the chance he might survive was unthinkable. After several more passes, fuel running low, they reluctantly turned west and returned to the Ryujo. The submarine assigned to rescue operations searched the waters around Akutan for hours before an American destroyer drove it away. Koga's body and his Zero remained alone in the Aleutian wilderness, 5,000 miles from Japan, waiting to betray every secret of the Empire's most feared weapon. 5 weeks passed with Koga's Zero sitting undisturbed in the Akutan bog. The crash site lay out of sight from standard shipping lanes and aerial patrol routes, hidden in a small valley that received perhaps 6 days of clear visibility per month through perpetual Aleutian fog. The carrier forces that might have searched for Koga had already retreated westward after the catastrophic defeat at Midway. The young pilot's fate became another casualty statistic in a war rapidly turning against Japan. On July 10, 1942, Lieutenant William Thies piloted a PBY Catalina patrol bomber through Aleutian weather that made navigation treacherous. Magnetic compasses were unreliable near the Arctic Circle, and landmarks disappeared beneath near-constant fog. Thies had been navigating by dead reckoning when he spotted the Shumagin Islands through a break in the clouds. Recognizing his position, he corrected course for Dutch Harbour, choosing to fly directly over Akutan Island, rather than around it to save time and fuel. Machinist Mate Albert Knack, serving as plane captain, happened to glance down at precisely the right moment. Through a temporary gap in fog, he spotted an unusual shape in the marsh below, something that did not belong in the Aleutian landscape. The bright red circles on the wings were unmistakable. Thies circled the site several times, carefully noting the position on his charts. The Zero appeared remarkably intact, a prize beyond imagination. He immediately returned to Dutch Harbour to report the discovery. Within hours, a recovery party landed near the crash site to assess what they had found. Their excitement was almost overwhelming. The Zero had landed in perhaps the only spot on Akutan Island where the bog was soft enough to cushion the impact while being firm enough to prevent the aircraft from sinking. The marsh had acted like a giant shock absorber, dissipating force that would have shattered the airframe on solid ground. Aside from a crushed windscreen, bent propeller tips, broken landing gear and damaged wingtips, the aircraft was fundamentally intact. The recovery team carefully removed Koga's body from the cockpit and buried him with military honours on a hillside overlooking the crash site. They noted the extensive medical taping around his torso, suggesting previous injuries or precautionary measures against high-acceleration manoeuvres. His personal effects were removed as intelligence materials. Then began the challenging task of extracting a fighter aircraft from an Aleutian bog. The recovery operation took nearly 3 weeks of back-breaking labour in some of the most inhospitable conditions on Earth. Workers constructed a makeshift road using logs and planking, slowly winching the captured fighter across half a mile of treacherous ground to the coast, where it could be loaded onto a barge. The entire operation proceeded in perpetual damp cold, with equipment that froze or rusted overnight. But the prize justified any hardship. By late July, the Zero had been loaded aboard a cargo ship for transport to the United States. The vessel departed the Aleutians in early August, sailing south through waters that weeks earlier had been contested by Japanese and American fleets. The captured Zero arrived in Seattle on August 1st, transferred immediately to a barge for the journey to Naval Air Station North Island near San Diego. The aircraft reached San Diego in mid-August, where it was unloaded under heavy guard and moved to a secure hangar. 24-hour military police protection ensured no souvenir hunters could damage the invaluable prize. Word of the capture spread through Navy aviation circles with electric excitement. For the first time since the Zero's devastating debut at Pearl Harbor, American engineers and pilots would have opportunity to examine the legendary fighter in detail. Navy Captain William Leonard, who would later command a carrier division in the Pacific, called it a treasure that unlocked so many secrets at a time when the need was so great. Marine Lieutenant Colonel Kenneth Walsh, who would survive the war as an ace with 21 kills, later stated that knowing what to do with a Zero on his tail, information that came directly from studying Koga's aircraft, saved his life several times. The restoration team worked around the clock, carefully documenting every detail of the aircraft's construction while simultaneously repairing crash damage. The work proceeded with astonishing speed, driven by urgency and recognition that this single aircraft might hold keys to winning the air war in the Pacific. Every day the aircraft remained grounded was another day American pilots faced an enemy they did not fully understand. The restoration revealed immediate insights into Japanese design philosophy. The Zero was built like a precision watch, engineers noted, with flush rivets throughout the airframe and guns mounted flush with wing surfaces to minimize drag. Every component was designed for minimum weight and maximum efficiency. The instrument panel displayed remarkable simplicity, with no superfluities to distract the pilot, just essential gauges arranged for instant readability. Inspection panels could be opened by simply pushing on marked spots with a finger, releasing internal latches. The entire aircraft could be disassembled and reassembled using minimal tools, crucial for field maintenance on primitive island bases. The team discovered the Zero weighed between 5,300 and 6,100 pounds fully loaded, depending on ammunition, fuel load, and configuration. This was roughly 2,000 pounds lighter than the American F-4F Wildcat. Extraordinary weight savings came from multiple sources. The Zero lacked armor protection for the pilot, relying instead on superior maneuverability to avoid being hit. Fuel tanks were not self-sealing, trading safety for reduced weight and increased capacity. The airframe itself used minimum structural material, just enough strength for anticipated loads with no safety margin. The Zero embodied a fundamentally different design philosophy than American fighters. Where American aircraft prioritized pilot protection and structural ruggedness, accepting weight penalties for survivability, the Zero sacrificed protection for performance. It was a fighter designed to win through superior agility rather than absorbing punishment. The captured aircraft revealed other secrets. The engine, a 14-cylinder Nakajima Sakai radial producing approximately 950 horsepower, used a float-type carburetor that would prove significant in combat. The wings folded for carrier storage using a simple manual mechanism requiring no hydraulic systems. Control surfaces were fabric-covered over metal frames to minimize weight. Most remarkably, the armament package was formidable for such a lightweight aircraft. Two 7.7mm machine guns firing through the propeller arc and two 20mm cannons mounted in the wings. By September 20th, just 41 days after arriving in San Diego, the Zero was ready to fly. The restoration team had replaced the crushed windscreen, straightened the vertical stabilizer and rudder, repaired wingtips and flaps, and completely rebuilt the landing gear that had been sheared off in the crash. The original three-blade Sumitomo propeller was carefully dressed and reused. The captured aircraft was repainted, red Japanese Hinomaru roundels covered with American blue circle and white star insignia. It looked like an American aircraft wearing Japanese clothes. Sanders had sat in the cockpit for hours, familiarizing himself with Japanese instruments, memorizing control layout, preparing mentally for a flight unlike any he had attempted. He was an experienced test pilot, but he was about to fly an enemy aircraft whose flight characteristics could only be guessed from intelligence reports and combat observations. If those reports were accurate, the Zero was faster, climbed better, and turned tighter than any American fighter. If those reports were wrong, or if the captured aircraft had hidden damage, he might not survive the first flight. On that September morning, Sanders climbed into the Zero's cockpit for the first time as pilot rather than student. Ground crew started the engine, which caught immediately and ran smoothly, vindicating the restoration team's work. Sanders taxied to the runway, conscious that dozens of engineers, intelligence officers, and Navy brass were watching from the tower and flight line. He advanced the throttle, and the Zero accelerated down the runway with surprising eagerness. The lightweight fighter lifted off after a remarkably short ground roll, climbing at a rate that would have been impressive in any American aircraft. For the next hour, Sanders put the Zero through performance tests, carefully exploring its flight envelope. He climbed to altitude, tested stall characteristics, practiced basic maneuvers, and felt out the aircraft's handling qualities. What he discovered in that first flight would change everything American pilots knew about fighting the Zero. Immediately apparent was the fact that ailerons froze up at speeds above 200 knots, making rolling maneuvers at those speeds slow and requiring much force on the control stick. The Zero rolled to the left much easier than to the right. The high-speed aileron problem was dramatic and unexpected. At low speeds, the Zero's maneuverability was everything Japanese pilots claimed, capable of turning inside any American fighter with ease. But above 200 knots, roughly 230 miles per hour, the ailerons became increasingly heavy and unresponsive. Fabric-covered control surfaces ballooned with air pressure at high speeds, requiring enormous stick force to overcome. American fighters, with their metal-covered control surfaces and hydraulic boost systems, maintained full control authority at all speeds. Sanders discovered a second critical weakness during negative acceleration maneuvers. When he pushed the stick forward sharply, inducing negative gravitational forces, the Zero's engine coughed and died. The float-type carburetor, designed for positive and zero gravity conditions, could not maintain fuel flow during sustained negative acceleration. The engine would restart when positive acceleration resumed, but for several seconds, the Zero became a powerless glider. This weakness had profound tactical implications Sanders recognized immediately. American pilots, being outmaneuvered and unable to escape a pursuing Zero, now had their answer. Go into a vertical power dive, using negative acceleration if possible to open range while the Zero's engine was stopped by the forces involved. At about 200 knots, roll hard right before the Zero pilot could get his sights lined up. The Zero could not follow either maneuver effectively. Sanders completed 24 test flights over the next 25 days, each one revealing additional details about the Zero's capabilities and limitations. He tested the aircraft at various altitudes, power settings, and combat configurations. He performed mock dogfights against American fighters, with other test pilots flying F-4F Wildcats and newer aircraft. The data accumulated from these flights was extraordinary. The Zero's maximum speed was slightly less than the F-4F Wildcat, contrary to combat reports suggesting the Japanese fighter was faster. Sanders speculated this might be due to reconstruction weight, as the restoration team had been unable to source exact replacement materials for some components. However, the Zero's exceptional range exceeded 1,900 statute miles, far surpassing any American carrier fighter. The aircraft could remain airborne for over 6 hours, enabling it to escort bombers deep into enemy territory or patrol vast expanses of ocean. The Zero's rate of climb exceeded American fighters significantly. Capable of reaching 20,000 feet faster than an F-4F could reach 15,000 feet. In turning combat at low speeds, the Zero could complete a full circle in time for American fighters to complete only 3/4 of a turn. These performance characteristics explained why early war combat had favored Japanese pilots so decisively. At low speeds and in turning fights, the Zero was simply superior to anything America fielded in late 1941 and early 1942. But Sanders' tests revealed these advantages came with exploitable weaknesses. The Zero's light construction meant it could not withstand battle damage. Hits that would merely damage an American fighter often proved fatal to the Zero, which lacked armor and self-sealing fuel tanks. Material analysis of captured Zero components revealed aluminum alloys of excellent quality, but used in thicknesses American designers would consider inadequate. The Zero was built to minimum tolerances, with no safety margins for combat damage. Sanders' final report synthesized all test data into actionable intelligence. American pilots should avoid slow-speed turning fights where the Zero's maneuverability dominated. Instead, they should use diving attacks, utilizing superior high-speed characteristics of American fighters. When a Zero pursued, American pilots should enter a steep dive, preferably with negative acceleration to kill the Zero's engine, then execute a hard right roll at high speed where the Zero could not follow. Team tactics should replace individual dogfighting, with wingmen covering each other and using coordinated attacks to negate the Zero's turning advantage. These recommendations were compiled and distributed throughout the fleet with unprecedented speed. Pilots preparing for combat received detailed briefings on the Zero's characteristics and how to exploit its weaknesses. The information was incorporated into training programs, with instructors teaching the high-speed dive and hard right roll technique to every new pilot. Combat veterans who had survived early encounters with Zeros suddenly understood what they had been fighting and how to win. The impact on pilot morale was profound. For 8 months, American naval aviators had faced an aircraft that seemed invincible, capable of outturning and outclimbing anything they flew. Pilots had developed a healthy respect for the Zero that bordered on fear. The official American tactic when jumped by Zeros had been simply to run away, a humiliating admission of inferiority. Now, for the first time, American pilots had concrete knowledge of how to fight the Zero and win. The mystique surrounding the Japanese fighter began to crumble. It was still a formidable opponent, but it was no longer invincible. It had weaknesses, and American pilots now knew exactly what those weaknesses were and how to exploit them. But the Akutan Zero's greatest contribution was not to tactical doctrine. It was to aircraft design, specifically to a fighter already under development when Koga crashed in the Aleutians. The Grumman F-6F Hellcat would become the weapon that transformed American tactical knowledge into devastating combat results. The connection between the two aircraft has been subject to historical debate, with some claiming the Hellcat was designed based on the captured Zero, while others note the timeline makes direct influence impossible. The truth lies somewhere between, a story of parallel development, timely intelligence, and Grumman's ability to incorporate lessons learned even as their fighter was entering production. In January 1942, Leroy Grumman sat at his desk reviewing preliminary designs for what would become the F-6F Hellcat, and the numbers troubled him. The Navy needed a fighter to replace the F-4F Wildcat, something faster and more powerful to counter reports coming from the Pacific about Japanese air superiority. Grumman's design team, led by chief engineers Jake Swerble and Bill Schwendler, had created what was essentially a larger, more powerful Wildcat. The design looked good on paper, but Grumman worried it might not be enough. Early months of 1942 brought increasingly alarming reports from the Pacific. American pilots were being outfought by Japanese Zeros at every encounter. The F-4F Wildcat, Grumman's current frontline fighter, was proving inadequate despite being a solid, well-built aircraft. Combat reports indicated the Zero could outclimb, outturn and outrange the Wildcat in nearly every performance category. Something dramatically better was needed, and needed urgently. Grumman's initial F-6F design, designated XF-6F-1, was planned around the Wright R-2600 Cyclone engine producing 1,700 horsepower. This would give the new fighter more power than the Wildcat's 1,200 horsepower Pratt & Whitney R-1830. But Grumman questioned whether it was enough of an improvement. The company had been developing the XF-6F1 since mid-1941, with formal contract signed on June 30, 1941, nearly a year before Koga's Zero crashed in the Aleutians. Design work proceeded rapidly through early 1942, driven by urgent Navy requirements and Grumman's recognition that the Pacific War would be won or lost in the air. The Bureau of Aeronautics worked closely with Grumman engineers, incorporating feedback from combat pilots returning from the Pacific. On April 22, 1942, 6 weeks before the Battle of Midway and 7 weeks before Koga's crash, Lieutenant Commander Edward O'Hare visited Grumman's Bethpage facility. O'Hare, fresh from combat operations in which he had single-handedly defended the carrier Lexington against Japanese bombers, earning the Medal of Honor, met with Grumman engineers to discuss the F-4F Wildcat's performance against the Zero. His insights were sobering. The Zero was faster than American intelligence had estimated, climbed better than seemed physically possible for its engine power, and could turn inside the Wildcat with ease. O'Hare emphasized that American fighters needed more power, better climb rate, and improved visibility for the pilot. The day before meeting with Grumman engineers, O'Hare had met with President Franklin Roosevelt during the Medal of Honor presentation ceremony. The president asked what was needed in a new naval fighter. O'Hare's response was direct and memorable: a plane that will go upstairs faster. Bureau of Aeronautics Lieutenant Commander A.M. Jackson, working closely with Grumman, directed specific design changes based on combat experience. Jackson emphasized mounting the cockpit higher in the fuselage, with forward fuselage sloping down slightly to the engine cowling, giving the pilot excellent visibility over the nose. He stressed to Grumman engineers that you cannot hit them if you cannot see them. These changes were incorporated into the XF-6F design before Koga's Zero was even discovered. On April 26, 1942, 5 weeks before Koga's final flight, the Bureau of Aeronautics made a critical decision that would define the F-6F's character. Based on combat accounts from the Pacific and O'Hare's recommendations, Buer directed Grumman to install a more powerful engine in the second XF-6F prototype. The Wright R2600 was abandoned in favor of the Pratt & Whitney R2800 Double Wasp, an 18-cylinder radial engine producing 2,000 horsepower. This was the same engine being used in the Vought F-4U Corsair and Republic P-47 Thunderbolt, and it represented a 50% increase in power over the original XF-6F-1 design. Grumman complied by redesigning and strengthening the F-6F airframe to handle the more powerful engine. The change required modifications to the engine mount, cooling system, and structural components throughout the aircraft. It meant delays in the development schedule, but performance gains would be worth it. Grumman estimated the new power plant would increase performance by 25% over the original design. The engine change decision came from multiple factors converging simultaneously. The R2800 had proven reliable in testing and was entering production for other aircraft programs. Pratt & Whitney could provide engines without the delays plaguing Wright R2600 development. Most importantly, combat reports indicated that incremental improvements would not be sufficient. American fighters needed a quantum leap in performance to match or exceed the Zero's capabilities. The first XF-6F-1 prototype, still fitted with the Wright R2600 Cyclone engine, made its maiden flight on June 26, 1942, with test pilot Bob Hall at the controls. This was 8 days before Koga crashed in the Aleutians and 6 weeks before the Zero was discovered. The prototype performed well, demonstrating good handling characteristics and no serious vices, but its performance with the 1,700 horsepower Cyclone confirmed Grumman's concerns that more power was needed. The second prototype, designated XF-6F-3 and fitted with the 2,000 horsepower R2800 Double Wasp, first flew on July 30, 1942. This was 20 days after the Akutan Zero was discovered, but 2 months before it would be restored to flying condition and tested. The XF-6F-3's performance exceeded expectations. The additional power transformed the design, giving it climb rate and speed needed to compete with the Zero on equal terms. But the Hellcat's development did not stop there. Throughout summer 1942, Grumman engineers continued refining the design based on ongoing combat reports and intelligence from the Pacific. When the Akutan Zero arrived in San Diego in mid-August, detailed technical data began flowing to the Bureau of Aeronautics and Grumman within days. The captured aircraft had not yet flown, but physical examination revealed crucial information about its construction, weight, armament, and design philosophy. This intelligence arrived at a critical moment in the F-6F's development. The basic design was set, the engine selected, and the first prototypes flying. But production had not yet begun, meaning changes could still be incorporated relatively easily. Grumman engineers studied the Zero data with intense interest, looking for ways to ensure their fighter could not just match but exceed the Japanese aircraft's capabilities. The Zero weighed between 5,300 and 6,100 pounds fully loaded. The F-6F would weigh over 12,000 pounds. This enormous weight penalty, more than double the Zero's weight, had to be compensated by additional power and intelligent design. Grumman's philosophy differed fundamentally from the Japanese approach. Where the Zero sacrificed protection for performance, the F-6F would provide both. Roy Grumman, the company's founder, made a key decision after studying the Zero data. He determined that Grumman could match or surpass the Zero in most respects without sacrificing pilot armor, self-sealing fuel tanks, and robust fuselage structure. The F-6F would compensate for extra weight with additional power from the R2800 engine. This decision shaped everything that followed. The F-6F would be built tough, capable of absorbing battle damage that would destroy a Zero. It would protect its pilot with armor plate behind the seat and bulletproof windscreen. It would carry self-sealing fuel tanks that could take hits without catastrophic fires. It would have redundant systems and robust structure capable of withstanding hard carrier landings and combat damage. The weight penalty would be overcome by raw power and intelligent design that made the most of available performance. Data from the Akutan Zero, combined with combat reports and Sanders test flights in September and October, influenced specific design decisions as the F-6F moved toward production. The F-6F's wings were designed for high-speed performance using a different airfoil and control surface design than the Wildcat. The ailerons were hydraulically boosted and metal-covered, ensuring full control authority at all speeds. This directly addressed the high-speed aileron problems Sanders discovered in the captured Zero. The F-6F would be able to roll effectively at speeds where the Zero's controls locked up. The F-6F's fuel system used a pressure carburetor rather than the float type used in the Zero. This ensured the engine would continue running under negative acceleration, eliminating the weakness Sanders had exploited in his test flights. An F-6F pilot could dive away from a pursuing Zero without his engine quitting at the crucial moment. The F-6F structure was designed to handle 9G positive and 6G negative acceleration, far exceeding the Zero's structural limits. This meant F-6F pilots could use aggressive maneuvers without fear of structural failure, while Zeros attempting to follow would risk breaking up. The armament package was increased to 650 caliber machine guns compared to the Wildcat's 4. Later versions would offer the option of two 20mm cannons and 450 caliber guns. The concentrated firepower could destroy the lightly built Zero with short bursts, while the F-6F's armored structure could absorb return fire. Visibility from the cockpit was exceptional, with the raised pilot position providing clear views in all directions. This addressed Jackson's emphasis that pilots could not shoot what they could not see. The design incorporated lessons from the thatch weave and other defensive tactics, recognizing that visibility was crucial for mutual support between wingmen. On October 3, 1942, the first production F-6F-3 made its maiden flight, just 2 weeks after Sanders completed his initial test flights in the Akutan Zero. The timing was not coincidental. Production had been deliberately delayed until engineers could incorporate the latest intelligence. The myth that the F-6F was designed based on the Akutan Zero is demonstrably false, given that basic design predated Koga's crash and the engine change decision came before the Zero was even discovered. But the timing allowed Grumman to refine the F-6F's final configuration based on knowledge gained from the captured aircraft. Pilot reaction to the new fighter was enthusiastic. After months of fighting in F-4F Wildcats, struggling against superior Japanese aircraft, the F-6F felt like a quantum leap in capability. It was faster, climbed better, had more firepower, better visibility, and felt solid in a way the Wildcat never had. Pilots quickly discovered the F-6F was remarkably easy to fly. Grumman had designed it specifically to be operated by relatively inexperienced pilots fresh from training, recognizing that wartime expansion would flood the fleet with newly minted aviators. The F-6F had no bad habits, no tricky characteristics that could kill an unwary pilot. It was stable, predictable, and forgiving of mistakes. Carrier landings, the most challenging aspect of naval aviation, were straightforward in the Hellcat. The robust landing gear absorbed hard impacts that would have collapsed lesser aircraft. The visibility allowed pilots to precisely judge their approach. The controls remained responsive at low speeds required for carrier approaches. Production ramped up with astonishing speed. Grumman built a new factory at Bethpage specifically for F-6F production, with first aircraft rolling off the line before factory buildings were even completed. At peak production in 1944, Grumman produced 644 aircraft in a single month, one Hellcat every hour, an aircraft production record never equaled. The scale was staggering. Each F-6F required approximately 20,000 individual parts sourced from hundreds of subcontractors. The Pratt & Whitney engines were built in 3 separate factories and shipped to Bethpage for installation. Grumman coordinated this industrial symphony with precision that amazed observers. Much credit went to Jake Swerble, Grumman's production genius who organized workflow and supply chain with unprecedented efficiency. The F-6F made its combat debut on August 31, 1943, 15 months after the Akutan Zero was discovered and 11 months after Sanders' first test flight. Aircraft from Fighting Squadrons 5 and 9, operating from carriers Yorktown and Independence, attacked Marcus Island as part of a carrier raid. The mission was an overwhelming success. No Japanese fighters managed to get airborne, and several were destroyed on the ground. 2 Hellcats were lost to anti-aircraft fire, but in air-to-air combat, the F-6F demonstrated immediate superiority. Over following months, the F-6F became the standard fighter on American fleet carriers, gradually replacing the F-4F Wildcat on large carriers, while Wildcats continued serving on smaller escort carriers. By early 1944, the Hellcat equipped 15 carrier fighter squadrons and was rapidly becoming the dominant American naval fighter in the Pacific. Tactical lessons learned from the Akutan Zero were incorporated into every aspect of F-6F operations. Pilots were trained to avoid slow-speed turning fights unless they had significant altitude or numbers advantage. Instead, F-6F doctrine emphasized high-speed slashing attacks, diving from altitude to build speed, making a single firing pass, then zooming back to altitude before the more maneuverable Zeros could respond. The Thatch Weave, developed by Lieutenant Commander John Thatch even before the Zero was captured, became standard defensive doctrine for all F-6F squadrons. When jumped by Zeros, F-6F pilots flew in mutually supporting pairs, weaving back and forth so that any Zero pursuing one F-6F would immediately face head-on fire from the other. The tactic neutralized the Zero's turning advantage by forcing the Japanese pilot to either break off or face a head-on engagement where the F-6F's superior firepower and protection dominated. Pilots were taught to use their speed and power to dictate engagement terms. If the tactical situation favored the F-6F, engage. If not, use superior speed to disengage, reposition, and attack from advantage. The F-6F's climb rate allowed it to regain altitude quickly after diving attacks. Its speed allowed it to escape from unfavorable situations. Its endurance allowed it to patrol longer and chase fleeing enemies farther than Zeros could follow. On November 23, 1943, over the Gilbert Islands, F-6F Hellcats from carrier Essex engaged Japanese Zero fighters over Tarawa in what would become the first major test of the new fighter against Japan's best. 30 Zeros rose to intercept the American strike, and the ensuing dogfight raged across the skies over the invasion beaches. When the smoke cleared, American pilots claimed 30 Japanese fighters destroyed for the loss of a single F-6F. The Battle of Tarawa demonstrated everything the F-6F was designed to accomplish. American pilots, many of them relatively inexperienced, had met veteran Japanese aviators flying Zeros and crushed them utterly. The combination of superior aircraft performance, sound tactics based on knowledge of the Zero's weaknesses, and intensive training had created an unbeatable formula. The battle's outcome sent shockwaves through both American and Japanese commands. For the Americans, it validated the F-6F's design and tactical doctrines developed from studying the Akutan Zero. For the Japanese, it revealed that American aircraft had caught up to and surpassed the Zero's capabilities. The age of Japanese air superiority was ending, but Tarawa was just the beginning. The F-6F would prove its worth in every major engagement across the Pacific for the next 20 months, compiling the most dominant combat record of any American fighter in World War II. June 19, 1944, in the Philippine Sea west of the Mariana Islands, F-6F Hellcats from 15 American aircraft carriers, 7 large fleet carriers, and 8 light carriers of Task Force 58 prepared to face the largest Japanese carrier aviation force assembled since the Battle of Midway 2 years earlier. The Japanese had 9 aircraft carriers and sent wave after wave of aircraft to destroy the American invasion fleet attacking Saipan. What followed became known as the Great Marianas Turkey Shoot, the most one-sided aerial battle in naval history. The first Japanese strike, 69 aircraft, lost 42 planes before reaching the American fleet. The remaining 27 that penetrated to the carriers accomplished nothing while facing a storm of anti-aircraft fire and swarming F-6Fs. The second wave, 107 Japanese aircraft, lost 97 before they could even attack. Japanese carrier aviation was being systematically destroyed. Throughout the day, Japanese carriers launched 370 aircraft in multiple strikes. Only 130 returned. The F-6F Hellcats, flying combat air patrol over the American fleet and hunting Japanese strike groups, shot down the vast majority. American losses totaled 23 to 30 aircraft, with many pilots rescued from the ocean. The strategic impact was catastrophic for Japan. The carrier air groups, painstakingly rebuilt after losses at Midway, were annihilated. The experienced pilots who had trained the current generation were dead. The aircraft that had been hoarded for the decisive battle were gone. Japanese naval aviation would never recover from this single day's losses. The Battle of the Philippine Sea demonstrated the F-6F operating at peak effectiveness. The aircraft's exceptional endurance allowed continuous combat air patrols over the fleet. Its climb rate ensured F-6Fs could intercept incoming strikes at optimal altitude. Its speed allowed pursuit of fleeing Japanese aircraft. Its firepower and protection meant that in any head-to-head engagement, the F-6F held overwhelming advantage. But perhaps most importantly, the F-6F's easy handling meant that even relatively inexperienced American pilots could operate the aircraft effectively in combat. By mid-1944, the United States was producing pilots far faster than Japan, and the F-6F allowed these new aviators to be thrown into combat with confidence they could survive and succeed. Japanese pilots, by contrast, were receiving increasingly abbreviated training as fuel shortages and instructor losses mounted. By late 1944, Japanese pilots were entering combat with perhaps one-third the flight hours American pilots received. The experience differential, combined with the F-6F's technical superiority, created a death spiral for Japanese aviation. Every engagement cost Japan irreplaceable pilots, while American losses were quickly replaced by the training pipeline producing thousands of new aviators annually. The F-6F's contribution to American victory extended beyond aerial combat. The aircraft was adapted into multiple specialized variants that addressed specific tactical needs. The F-6F-3N and F-6F-5N night fighter variants carried radar equipment in a pod mounted on the starboard wing, allowing them to intercept Japanese night bombing raids. The radar reduced top speed slightly, but night fighter pilots found the capability worth the trade-off. F-6F night fighters achieved remarkable success against Japanese night raiders, shooting down bombers that had previously operated with impunity. Later, F-6F-5 variants were modified to carry 2,000-pound bombs on a centerline rack and rocket rails under the wings, transforming the fighter into a highly effective fighter bomber. F-6Fs armed with bombs and rockets provided devastating close air support for Marine and Army forces fighting across Pacific Islands, attacking Japanese bunkers, artillery positions, and troop concentrations with precision that artillery could not match. By the end of World War II, F-6F Hellcats had compiled statistics that remain unmatched by any other American fighter. The aircraft was credited with destroying 5,163 enemy aircraft in air-to-air combat by United States Navy and Marine Corps pilots, an additional 60 aircraft destroyed in other theaters, bringing the total to 5,223 when including British Royal Navy Fleet Air Arm victories. Only 270 F-6Fs were lost in air-to-air combat, giving the aircraft an overall kill-to-loss ratio of 19-1. Against Japanese Zeros specifically, the ratio was 13-1. These numbers reflected the combined impact of superior aircraft performance, sound tactical doctrine derived from studying the Akutan Zero, and increasingly skilled American pilots facing declining Japanese opposition. The F-6F produced more fighter aces than any other Allied aircraft of World War II. Between 305 and 307 Navy Hellcat pilots achieved ace status with 5 or more victories, with slight variations in counts depending on how shared kills were attributed. The Navy's top ace, Commander David McCampbell, scored all 34 of his victories flying F-6Fs. The Hellcat's combat record was so dominant that late-war Japanese pilots developed what American intelligence called zero fatigue, a recognition that engaging F-6Fs was likely to be fatal. Japanese pilots increasingly avoided combat when possible, diving away or fleeing into clouds rather than fighting. This psychological dominance was as significant as the technical superiority, as it allowed American carrier groups to operate with near impunity, knowing Japanese air opposition would be minimal and ineffective. The contrast with early war combat was stark. In 1942, American pilots had fled from Zeros whenever possible. By 1945, Japanese pilots were fleeing from Hellcats. The transformation was complete. The Akutan Zero's role in this transformation cannot be precisely quantified, but its importance is undeniable. The captured aircraft provided the first detailed intelligence on the Zero's capabilities and limitations. Sanders' test flights revealed specific weaknesses that could be exploited tactically. The technical data influenced F-6F design decisions at a crucial moment when changes could still be incorporated. Most importantly, the Akutan Zero destroyed the mystique surrounding the Japanese fighter, proving it was not invincible, but rather an aircraft with specific strengths and specific weaknesses. The combination of the F-6F Hellcat and tactical knowledge gained from the Akutan Zero created a synergy that transformed American naval aviation. The F-6F was not designed because of the Akutan Zero, but it was refined based on intelligence from the captured aircraft. The tactics American pilots used were not created by studying the Zero, but they were validated and formalized by Sanders' test flights and subsequent analysis. The result was an integrated system of aircraft, tactics, training, and industrial production that overwhelmed Japanese aviation. By war's end, Japan had produced approximately 10,500 Zeros, their primary fighter, throughout the conflict. The United States produced 12,275 F-6F Hellcats in 37 months, plus thousands of F-4U Corsairs and other fighters. The production differential reflected America's industrial might, but the combat differential reflected the F-6F's technical superiority and the tactical doctrine that employed it effectively. The Akutan Zero was destroyed in February 1945, ironically in a training accident rather than combat. While taxiing for takeoff at Naval Air Station North Island, an SB-2C Helldiver dive bomber lost control and crashed into the parked Zero, its propeller slicing the Japanese fighter into pieces. William Leonard salvaged several gauges from the wreckage, donating them to the National Museum of the United States Navy. The Alaska Heritage Museum and Smithsonian National Air and Space